And welcome back to a second video on dewatering. So this time we will be looking at two quick examples. One is the dewatering, or the drawdown in the middle of a circle shape. So if we do a circle of wells, right, multiple wells in a circle, what is the drawdown at the center of the well? And then we'll do examples where we have line of wells, and we'll see how we can use the math basically, or geometry of that, to calculate dewatering at a construction site. So this example is for a circle of wells. On the top right here, you can see the illustration of the circle of wells and the nomenclature. So SC is the drawdown in the middle, in the center of the circle. A is the radius. SW is the drawdown in the well, in a well. And then SM is the drawdown midway through, in between two wells, basically midway between two of the wells. This example is taken from Charbonneau and was worked out by Jacob, 1950. So assuming that each well pumps at the same rate, so if you remember from the last video, right, when all the wells pump at the same rate, it makes the math much easier. Then the drawdown at the center is 2 pi ts over q, sum of natural log of the ratio of the radius of influence divided by the radius of interest, right, Ri. So again, Ri is the distance from the circle to the center. So what I call A here, and this is Ri as well in our case, right? So this is again the radius of interest, meaning, this is the distance to the middle of the circle, which is where we want to know what the drawdown is, because we're designing, let's say, for a construction site there. Since NQ is the Q total, right? So then if they all pump at the same rate, right, I can multiply, let's say, 10 liters per second. If I have 10 wells, right, the total discharge, or the total pumping rate, is 100 liters per second, right? So it's just the multiplication. You can calculate the total required discharge for a desired drawdown. So that's really the interest where it becomes design is, okay, well, if I want 2 meters of drawdown, right, so I can excavate, how much pumping do I need? Once I know how much pumping do I need, I can say, well, how many wells, is this, right? Depending on the pumps you have available. Let's say you need to use, 1 horse pumps, then you can say, okay, I need 10 pumps or 10 wells, right? Okay, so by geometry, basically just using geometry and trigonometric analysis, right, or essentially just geometry, we can arrive at this equation here that the drawdown in the well is the drawdown in the center plus discharge over 2 pi t log Ri over Rw. And then finally the drawdown in the middle of the wells, right, that might be of interest, also obtained by geometry, is the drawdown in the center minus Q over 2 pi t, natural log of 2. Okay, so now we have equations basically that we can use to design pumping, right, a well field to dewater, somewhere in the middle. And we'll do an example as an activity of this. So here is a little worked out example that you can, confirm, work out on your own. But if you have two wells that are located 100 meters from each other and both pump at 550 cubic meter per day, assume the radius of influence is 1,000 meters and the transmissivity for this aquifer is 100 square meters per day. If there's an observation well 75 meters perpendicular to the line between the two wells, calculate the drawdown in the observation well. Okay, so here's an example. So now we're switching to our line of wells, right? So we have two wells. That are 100 meters apart. And then we have the observation well, or let's say this is the place we want to dewater, for example, 75 meters perpendicular to the line. Okay, so now we can calculate R, which is the distance, right, from the center to the two wells, is the square root, right? You just use Pythagorean thing, so 50 square plus 70 square, or square root of that, that's 90 meters. So it's, this well here is 90 meters from either well, from the circle. And now we can use our equation. So the drawdown equals, n times q over 2 pi t ln r over I. We are given that the radius of influence is 1,000 meters in this example. Again, we have an equation that we can, calculate or estimate the radius of influence if we have time, but for now it's just given to you, so just use it. And then you can just, plug all the numbers and find that the drawdown is 4.2 meters. Okay, so this example here is an approximation for a line of well. So you can see here, remember those mini points, right? So if we have a bunch of wells in a line, now we can approximate the drawdown at some distance away. So again, we'll do the same example we just did, obviously with a simple case of two wells. And now we do a line of well approximation to see the difference. Here there's two equations. One is for confined, one is for unconfined per our usual procedures. And you can see, these get a little tricky with the inverse tangent intervenes, and then the natural log of, again, R would be the radius of influence. And you have the geometry, shown here. So L is the distance or the size of the line, if you will, right? The distance between the two extremes. Then A is the distance between two wells, and B is the distance perpendicular to that line to the center. So again, remember those graphics for the well points, or a line of well on the side to dewater, and then you do a little coffer dam on the other side to maintain, to avoid seepage. And then you can just use those equations, right, to find the dewatering. So here's the same example as before, right? The two wells 100 meters apart. Again, same radius of influence, same aquifer, so 100 square meters per day. Again, 75 meters perpendicular, so little b is 75 meters. Calculate the drawdown in the observation well, which is we just did in the previous slide, so 4.21 meters. Okay, so now what the point is, we can use the approximation, and here we'll use the confined aquifer approximation, assuming it's pumping in a confined aquifer. And here's the equation, right? So we have 4 pi Ts over Q total equals 4.77, right? Using this approximation, which means that S, so now we say S equals 4.77. Excuse me. Let me write this a little better, if I can. Pi t. Okay, so we know the numbers. So again, plugging all the numbers, we find that S using this approximation is 4.18 meters. So you can see that we only off by 3 centimeters. So this, again, this line of wells approximation is is a good approximation essentially to the problem, right? So you can see that using both methods we find the same result. Okay, I think I'll leave it here for these couple examples. We'll do an activity, asking you to kind of go through those equations again. But yeah, that's an example of how you can design dewatering for a construction site when you have to excavate. Thank you.